Good afternoon once again.
Good
Uh,
afternoon.
Present on the topic, explain the characteristic of dilatant flow and its example. Then, what is dilatant flow? Dilatant flow, also known as shear thickening flow, is a non-nonlinear fluid behavior where the viscosity of a fluid increases with increasing shear rate or applied stress. In other words, the fluid becomes thicker or more resistant to flow as it is stirred, shaken, or subjected to a greater force. This is due to the rearrangement of particles in the fluid, which cause increased particle interaction and resistance to deformation. Common examples include concentrated suspensions like cornstarch in water, or certain polymer solution. Then what are the applications in pharmacy? Suspension formulation. Dilatant flow is relevant in pharmaceutical suspension, where high solid content may exhibit shear thickening behavior. Understanding this property helps in designing formulations that remain stable during storage but flow appropriately during administration. Example, high concentration suspension of hard pharmaceutical ingredients may require specific mixing or dispensing techniques to manage increased viscosity under shear. Then cream, na application in cream and ointment. Some topical formulations such as cream or gel with high particulate content may display dilatant property. This affects their spreadability and application, ensuring they stay in a place where applied but resist excessive flow under high shear, that is during rubbing. Then drug delivery system. In controlled release system or injectable depot formulation, dilatant behavior can be engineered to control the release of rate drug. For instance, shear thickening material can be used to create gels that solidify under injection stress, forming a depot for sustained drug release. Then we have processing and manufacturing. During pharmaceutical manufacturing, e.g. mixing, pumping, or filling, dilatant flow can impact the handling of higher concentration slurry or pastes. Equipment must be designed to accommodate increased resistance under high shear to prevent clogging or uneven mixing. Example, processing of tablet granules or capsule filling with high solid content requires carefully control to avoid shear thickening issue. Then stability test. Dilatant properties are considered during stability studies of emulsions and suspension to ensure that the product maintain desired flow characteristic under various conditions, that is shaking or transport. Then you are using body armor and protective gel, that is liquid armor. Dilatant materials such as shear thickening liquid like silica particles suspended in polyethylene glycol are integrated into fabrics to create flexible body armor under high impact conditions, e.g. bullet or stab. The fluid instantly hardened despite the force and enhancing protection while remaining soft and flexible under normal condition. Then they are also used in sports equipment. Dilatant materials are used in padding for sports gear, e.g. shin guard, helmet, to absorb the space impact energy, reducing injury risk. Industrial application. Dilatant fluid are employed in machinery mounts, automotive suspension system, and sanitary damper. The ability to stiffen under rapid stress helps absorb vibration and shock, protecting equipment and structure. Then medical and orthopedic device. Prosthetic and orthotic. Dilatant materials are incorporated into braces, splints, and prosthetic liners to provide adaptive support. They remain soft for comfort during normal use but stiffen under sudden stress to stabilize joints or limbs. wound dressing. Then some experimental dressing are use dilatant property to conform to wound softly but harden to protect against external pressure. Then automatic and aerospace. We have crash protection, tight technology, and they are also using robotic and soft actuators. Dilatant material are used in soft robotic to create adaptive reflex or actuators that can switch between flexible and rigid states. This enables robots to handle delicate objects softly but grip firmly under applied force. Then they are using 3D printing and manufacturing. Dilatant fluids are investigated as smart material in additive manufacturing. Their shear thickening properties allow precise control during extrusion, enable complex structure with variable stiffness. Then they are used in military and defense, then arts and the design. Now, what are the characteristics of dilatant flow? Shear rate, shear thickening behavior. The hallmark of dilatant flow is its shear thickening behavior. As the shear rate increases, the velocity of the fluid rises, often dramatically. This is due to the formation of transverse particles clustered by hydrocluster, which resist flow. This relationship between shear stress and shear rate. Then volume dilation. Dilatant fluids often exhibit volume dilation under shear as particles are forced into closer contact, causing the material to expand. This dilation contributes to the increased resistance to flow and is a key feature of suspension like coaster in water. Then we have the reversibility. Dilatant behavior is typically reversible. Once the shear stress is removed, the fluid returns to its original state, provided no permanent structure change occur. This reversibility makes dilatant materials sustainable for applications requiring temperature
Grace, are you
stability.
with us?
Then dependence on particle concentration. The degree of dilatancy depends on the concentration of particles in the suspension. The higher particle concentration enhance shear thickening behavior due to increased particle interaction. Then you have sensitivity to shear rate. Then we talk about examples of dilatant flows in nature and industry. We have cornstarch suspension. A classic example of dilatant flow in a mixture is a mixture of cornstarch and water, often called oblque. At low shear rate, oblque flow like a liquid, but under a rapid deformation, it is striking it. It behaves like a solid due to the shear thickening. This behavior arises from the formation of particles cluster that resist flow. And then we talk about the geological system. In geophysics, certain granulous materials such as wet ground or quicksand exhibit dilatant behavior under shear. This property influence soil mechanism and landslide dynamic. Then application of dilatant material. Protective gear, industrial processing, shock absorption, um, educational demonstration, vibration dam, and 3D printing, as I've explained earlier. Then geotechnical engineering. That in our daily life now, in daily life, dilatant flow is most familiar through playful example like oblque, that is a cornstarch with water mixture, which demonstrate shear thickening by transitioning from a liquid to a solid like state under pressure. This phenomenon has practical application in household products and educational demonstration. For example, dilatant materials are used in some shoe insole or grip that stiffen under stress to provide support or enhance traction. In food processing, Understanding dilatant behavior is concentrated suspension like source or dove help optimizing mixing and packaging process. Moreover, dilatant flows inspires team education as and on experiments with shared technique fluid engage students in learning about rheology and material properties. Then advantage and disadvantage of dilatant flow. Advantage impact resistance and energy absorption, self-adaptive behavior, enhanced stability in suspension, tunable mechanism property, novel application in smart material. Then the disadvantage, difficulty in processing and handling, unpredictable behavior in complex system, limited range of application, material wear and tear, cost and complexity of formation. Um, then we talk about the challenges and limitation. Processing difficulties, that is the challenges. Predictability, material degradation, limited application. Then a case study, dilatant fluid in body armor. A notable application of dilatant fluid is the liquid body armor. Researchers have developed shear thickening fluid that remain flexible under normal conditions but adding upon impact, offering superior protection compared to traditional material. A study of Wagner and Bragg demonstrated that this fluid can absorb and dissipate energy effectively, reducing injury risk. Then the future research will talk about the microstructural analysis, material design, modeling improvement, and sustainability. Then in conclusion, dilatant flow characterized by an increase in viscosity with increase with shear rate. As a fascinating non-linear fluid behavior observed in shear thickening material.
Is that to not clap? Clap for him now. With this now, if you are asked now to talk about dilatant flow, can't you talk about it? Yeah? Even if you are not ready with this explanation, won't be able to talk about it? I believe you can, right? So, do you have any question for him? Any question? Any question? Ask.
When you're talking about the types of non-Newtonian fluids,
Sorry?
you said dilatant, if they remove the force applied to it, can return back to its original state. That's what I said. But I remember when we were doing this in class, there's another class, I can't remember, is it reopetic or that what I know about dilatant is that it's shear thickening as there's increase in shear with the viscosity increase. Then is it reopetic or there's one that if you now remove the shear rate, or maybe because we have not concluded that class because we're seeing that handout was confusing. But I knew that is one was telling us that when we remove the force, it will go back to its original state. Does it not mean that dilatant too can go back to its original state?
I think. Okay, sorry. It's a question. Answer the question. Sorry, I forgot.
Read the question again. I thought you were asking the lawyer.
What I know about dilatant.
Okay, what you're asking that when force is being applied to dilatant, will it go back to
its original? Once
when
the
the
force
force
applied to it is removed,
yes.
will it go back to its original state, viscosity?
Yes.
But when we're doing this in class, I think there's one that it will now go back to its original state, but it was not dilatant.
I said it's dilatant.
Okay. Now, let me comment. You have answered that it will go back. Now, let me if you can answer this question, and then, is there anyone that is shear thinning,
There's shear thickening.
and there is there shear thickening?
There's shear thickening and shear thinning.
So
Thinning.
now, whether shear thickening or shear thinning, will they both still go back to their original this, if the external force is removed?
Yes, it will.
It may be that one you're talking about. What's his name? Oh, that one.
There's one.
Because of course we agree that if it is shear thickening, external force will make it to do what? Become what? Viscosity will increase. But there are the ones that external force will make the viscosity to do what? To do what? Go down, right? That is shear thickening.
It's buopathic that we said that is like dilatant. It's shear thickening, but once the force is removed, it will return back to its original viscosity.
Okay.
Then we now said pseudotropic is like the pseudotropic is like pseudoplastic. It's shear thinning. But once the force is removed, it goes back to the original viscosity.
Okay, are you saying that dilatant?
But I understand. What I know about dilatant is that it's shear thickening, increase in shear rate.
Let's go practical and continue.
Increase in shear rate increases viscosity. So what I'm asking now, based on what he said.
Example. Okay, sorry. Example of the dilatant is what?
We have corn flour, starch and water.
Starch and water.
Yes.
Okay. Okay.
Corn flour in water. Potassium silicate in water.
What? Potassium
silicate in water.
Okay. Let's use corn starch in water now. Okay. If you apply, if you stir it, right, apply this, what will happen? Will it thicken?
Yes.
If it stop, will it go back to its original state?
If it stop.
Should
we use it like should we say like our pap now?
If you remove the shear force,
it will go back.
It will go back.
Yes.
That's
why this geology is still confusing me. Yes. Because today we are saying this, tomorrow we are saying, because that is my own knowledge. Because the handouts we had before, and you said it was confusing actually, but we have not yet gotten the right one now. Because the handout was saying dilatant.
Okay, check it up now. Leave that one. Check it up now.
On God.
You just check it up and see. Let's see.
Okay,
you are the master here now. Check it up and let us
Yeah,
know.
check it.
I want us to.
No, that one you are talking about.
I want you to check yourself.
Focus on that one that you raised, that issue. Okay, fast. Check both of them.
Okay.
Fast. No time.
Wow.
Fast, no time. You see anything? Okay.
Checking now.
Okay.
Fast.
So what do you want to check?
The difference between dilatant and buopathic flow.
Difference. Dilatant and what?
Buopathic.
peptic fluid.
Is that what?
Only telling between, I'm only saying reopetic, and it's talking about, it's saying that reopetic is shear thickening, but it's not telling me that once the force is removed, it will go back to the original state. But I'm not seeing anything on dilatant.
Okay. What your source of information for the dilatant is what?
Yeah.
Your information for the dilatant. What's your source of information? For the dilatant.
Saying that dilatant
Is what?
and reopetic fluids are both types of non-Newtonian fluids, meaning their viscosity changes with applied shear stress. Dilatant fluids, also known as shear thickening fluids, increase in viscosity as the shear rate increases, becoming more resistant to flow under higher stress. Reopetic fluid, on the other hand, increase in viscosity over time when subjected to a constant shear stress. I'm not seeing any difference.
Read the first paragraph again.
Dilatant, also known as shear thickening.
Also known as
shear thickening
okay.
fluids, increase in viscosity as the shear rate increases, becoming more resistant to flow under higher stress. Reopetic fluids, on the other hand, increase in viscosity over time when subjected to a constant shear stress.
This is exactly what this is exactly what we discussed in the last class. Is what we discussed in last class. I said that I said that the other one, the second one you mentioned, that one is time dependent.
That one, what is
It doesn't
the first is
constant. It's just the time. As the time increases, is there. But for that time, you need to increase the. Even if it may be within short period of time. What matters is that the force is high. If you increase the force, the force will be increasing. Both of them they are shear thickening, but this one is the first that is not time dependent, and the force must be increasing, not with constant. Is that clear now?
Yes.
Are you okay with it now? So
that means that other one too will be the other one that is similar to pseudoplastic too will be at when the shear stress is constant.
yes.
But both of them can return back to the
original. Yes.
Okay.
You are okay. You are not ready, right? Yeah. Okay. All right. Thank you very much.